Welcome students. Today we will discuss processing of legumes. Legumes are ripe seeds of the plant family Leguminaceae. The term pulses are limited to crops harvested for dry product only, excluding therefore crops harvested green for forage, used for grazing or as green manure, and also crops harvested green for food. They also exclude those used mainly for extraction of oil and crops whose seeds are used exclusively for sowing purposes such as alfalfa and clover. Pulses constitute an important source of dietary protein for large segments of the world's population, particularly in those countries in which the consumption of animal protein is limited by non-availability or is self-imposed because of religious and cultural habits. Pulses provide energy, dietary fiber, protein, minerals, and vitamins required for human health. Recent research studies suggest that consumption of pulses may have potential health benefits, including a reduced risk of cardiovascular disease, cancer, diabetes, osteoporosis, hypertension, gastrointestinal disorders, adrenal disease, and reduction of LDL cholesterol. However, legumes contain several anti-nutritional factors in the raw seeds that need to be reduced by processing so as to enhance the digestibility and nutritive value. Processing of legumes. The processing of food commodities generally implies the transformation of the perishable raw commodity to value-added product that has greater shelf life and is closer to being table ready. The common methods for processing of legumes include soaking, cooking, germination, fermentation, parching, besides canning, milling, flour making, extrusion, and fractionation. Soaking. Soaking of legume seeds in water is used to moisten and soften the seeds to reduce cooking time, aid in seed coat removal, and an aid in germination. Soaking reduces the toxin content and surface contamination. Soaking time varies with variety and species and with length and conditions of storage. High temperature soaking accelerates hydration. Cracking or scoring seeds with tough seed coats before soaking assists moisture uptake. The degree and rate of hydration of the storage protein matrix influences the cooking rate and final texture of cooked beans. The content of total soluble sugars and soluble minerals in legume decreases during soaking because of leaching losses. Germination. The germination process involves initially soaking the whole unhusked grains for 12 to 24 hours and then spreading them on a damp cloth for up to 48 hours. Under tropical conditions, sprouts up to a length of 1.0 cm appear. Sprouted grains are eaten raw with salt or further seasoned and fried or boiled. The direct effect of sprouting on both the physical and chemical changes and the nutritive value of legumes is of great interest. Chemical changes occurring in sprouted legumes primarily involve the carbohydrate of the grain, namely the conversion of some starch to lower molecular disaccharides and dextrins by the action of amylases. Increases in proteases also occur during germination, causing the degradation of high molecular proteins to lower molecular ones. It has been reported that protein content of raw beans slightly decreases from 28.1 to 26.7% in the germinated beans, the decrease being a result of protein breakdown by the proteolytic action of enzymes. Germinated beans had increased amounts of these essential amino acids: lysine 24%, threonine 19%, alanine 29%, and phenylalanine 7%. Ascorbic acid content has been reported to increase from a trace amount to 10 to 12 mg per 100 gram in the legumes germinated for 48 hours. Increases in thiamine, riboflavin, niacin, pyridoxine, biotin, tocopherol, choline, and available iron have also been reported during germination of various pulses, including chickpeas, pigeon peas, lentils, and mung beans. Cooking. It is probably the oldest domestic method of processing for making legumes edible. Usually, it includes a prior soaking of the seeds and subsequent cooking in boiling water until they become tender. Cooking of legumes can be done under ambient conditions, under pressure, or by the use of microwaves. Ordinary cooking. Generally, the pulses are added tap water and are cooked on a hot plate or cooking stove for 15 to 120 minutes or more until tenderness of the legumes is achieved. Pressure cooking. Pulses are often cooked in a pressure cooker for faster cooking in order to save time. It involves both high temperature and pressure treatment for a short duration and enhances the digestibility and palatability of legumes considerably. Pre-soaked legumes are subjected to pressure cooking for reducing the processing time and also for obtaining a tender product. Microwave cooking. It is a popular means of cooking in the urban areas for saving both energy and time. This form of cooking is even faster than pressure cooking, but it is limited to a higher strata of the society in the developing countries due to the high cost of the microwave oven and requirement of electricity for its working. Generally, the cooking treatments cause significant decreases in fat, total ash, carbohydrate fractions, anti-nutritional factors, minerals, and B vitamins. Cooking treatments decrease the concentrations of lysine, tryptophan, total aromatic and sulfur-containing amino acids. The losses in B vitamins and minerals in seeds cooked by microwave are smaller than those cooked by boiling and pressure cooking. In vitro protein digestibility, protein efficiency ratio, and essential amino acid index were found to be improved by all cooking treatments. Fermentation. Fermentation is probably one of the oldest methods for processing food grain legumes. Fermentation of food legumes is common in Asia and Africa. During fermentation, breaking down of carbohydrate into acid as the final end product by the action of microorganisms takes place. Examples of processed legumes using fermentation are idli, dosa, temp, natto, soya sauce, etc. The main effect of fermentation is to make more of the grain nutrients available for assimilation in the body, as the digestibility of the legume protein is increased. Digestive enzymes produced by microorganisms during fermentation are able to break down protein into amino acids and other water-soluble products of protein decomposition. In addition, it has been reported that the fermentation process inactivates unfavorable substances, including trypsin inhibitors, heme agglutinins, and saponins that are associated with edible legumes. This relates to the heating process involved in the preparation of fermented products. The natural formation of antioxidants during the fermentation process has also been reported. In addition, fermented products have an increased storage life at room temperature, since organic acids and the amino acids produced during the process can prevent contamination by pathogenic bacteria and microorganisms. Increases in choline and folic acid have also been observed in fermented preparations. Roasting. Roasting, also known as toasting or parching, is a form of preparing legumes. It is practiced mainly in India and Africa. Roasting refers to the method in which usually whole, husked or unhusked grains are exposed to dry heat. This is performed either directly by placing the whole grains and beans directly upon fire, or more commonly in hot common salt or sand that are in contact with the fire. Use of powdered common salt as heating medium is nowadays more common than using sand. Roasted legumes are generally consumed as snacks. Puffing. Puffed grain legumes are prepared in the Indian household in a manner similar to that used for roasting. It is nowadays commonly used at industrial level. Puffing brings about a light and porous texture. Whole unhusked grains are more commonly used for this process. For puffing, grains are soaked in water and mixed with sand, which has been heated to 250 degrees Celsius and then toasted for a short time, approximately 15 to 25 seconds. After the sand is sieved off, the grains are dehusked between a hot plate and a rough roller. The more common legumes prepared in this manner are chickpeas and peas. These products are traditionally eaten either with parched cereals or as a snack. Study with chickpeas indicated that moisture conditioning either by soaking or by the addition of water to the grains prior to heating is responsible for good puffing. Frying. This method of processing can be applied either at domestic or industrial level. Frying is mainly used on previously processed legumes, which are in the form of soaked grains, flour, paste, batter, or dough. Frying takes place in an open kettle that contains hot oil. In India, chickpea, black gram, and peas are often prepared into dough or paste, which are deep fried into crispy products. For example, papora from besan. In addition, mung bean or dal is also fried in a little fat and eaten as a snack. Canning. Canning is the preservation of food in hermetically sealed containers, usually till cans, and subsequently heat processing of the cans. Since the food is placed in airtight cans and heat processed for destruction of microbes, the contents of can remain preserved as further microbial entry into the can does not occur. Canning represents the most common method of processing legumes for human consumption, especially in the developed countries. It is done on a commercial basis since the process itself involves considerable time and the need for cooking kettles and can sealing equipment. Industrial canning overcomes the long time and high fuel costs involved in home preparation of legumes. Generally, common beans, lima beans, green or golden pea, and black-eyed pea are canned. Canning operation involves use of dried whole legume seeds, which are then washed in cold water. After draining, the seeds are allowed to soak overnight in water, during which time the moisture content of the dried seeds increases from an initial 10 to 12% to approximately 20%. This facilitates cooking of the whole seeds since there is softening of the seeds. After a weighed amount of beans are put in each can, a liquid is added to the can, this being either a thin sauce in the case of navy beans or water in the case of peas. The cans are then sealed on a double simmer and subsequently placed in a retort for cooking. The heat processing setup proceeds for a time that is dependent upon the temperature and pressure used. Since the retort is essentially a large pressure cooker, a shorter cooking time for processing the seeds can be used than is possible during cooking at atmospheric pressure. Milling of pulses. Milling of pulses is done at industrial level. Dry whole seeds of pulses have a fibrous seed coat. The seed coat is often indigestible. Therefore, pulses are mainly consumed after dehusking to improve their palatability, taste, and cooking properties. In most parts of the world, pulses are traditionally consumed either in the whole or in the form of dehusked split pulse. Dehulling, therefore, is an important primary processing activity. Milling of pulses involves removal of outer husk and splitting the grain into two equal halves. Generally, the husk is much more tightly held by the kernel of some pulses than most cereals, causing dehusking of pulses a problem. Conventional milling of pulse involves following steps: cleaning and grading of pulses. Cleaning of pulses involves removal of foreign material like chaff, sand, stones, mud, ferromagnetic materials, etc. from pulse grains. This is accomplished by exploiting differences between size, shape, density, and ferromagnetic properties of impurities and pulse grains. Grading is generally done on the basis of size using sieves of specific perforations, but it can also be done on the basis of color and absence of visible damage. Pitting. Pitting involves cracking and scattering of clean pulses by passing through emery-coated rollers. The clearance between the emery roller and cage gradually narrows from inlet to outlet. Cracking and scratching of husk takes place mainly by friction between pulses and emery as the material is passed through the narrowing clearance. Pre-treatment with oil. Scratched or pitted material is treated with some edible oil such as linseed oil at the rate of 1.5 to 2.5 kg per ton of pulses. This is done by passing it through a screw conveyor which helps in mixing of oil with pitted material. Then they are placed on floors for about 12 hours to diffuse the oil. Conditioning. This is done by alternate wetting and drying. About 3 to 5% water is added to the pulses after sun drying for a certain period, and then tempering is done for about 8 hours. The grain is dried in the sun again by allowing water to drop from an overhead tank on the pulses, which are passed through a screw conveyor. An addition of moisture to the pulses is achieved. The screw is slowly rotated 50 to 70 rpm to achieve proper mixing of oil water with the grain. The length and width of the conveyors range between 150 to 250 cm and 20 to 30 cm respectively. Until all pulses are sufficiently conditioned, the whole process of alternate wetting and drying is continued for 2 to 4 days. Pulses are finally dried to about 10% to 12% moisture content in sun or by mechanical hot air drying. Dehusking and splitting. Dehusking is a process that removes husk from the whole pulse seeds, improves appearance, texture, cooking quality, palatability, and digestibility of grains. In India, carborundum emery rollers are used for dehusking. The split pulses are then separated by sieving and the husk is aspirated off. Unsplit dehusked pulses and tail pulses are again dehusked and milled in a similar way. Until the remaining pulses are dehusked and split, the whole process is repeated 2 or 3 times. Polishing. Polishing is done to provide luster and improve the consumer appeal, and usually a screw conveyor is used for this operation. Depending on the consumer need, different polishing materials such as water, oil, or soapstone powder are applied to the split surface. Products can then be packaged for consumption. Pulse flour milling. Cleaned whole or dehulled seed or dehulled split seeds are ground into flour using a hammer, pin, and roller mill. Consumers usually prefer dehulled pulse flour as the bitter flavor typical of pulses is minimized. The flour is then packaged and sold to either the retail or ingredient supply market. Chickpea flour, commonly known as besan, is used in the production of papura in India. Pulse flours have been increasingly used as functional ingredients in bakery and meat products. Extrusion. Extrusion technology has been used recently for processing of legumes at industrial level. The extruded products are generally blends of cereal and legume flours. It involves the application of both pressure and heat. Products can be extruded at high temperature 140 to 200 degrees Celsius, high pressure 60 to 80 bars, with moisture content less than 20%. The cooking of the products is accomplished in a short time, 30 to 60 seconds. Forced out of the extruder through a variety of dyes and dried quickly as it has lower moisture content than conventionally processed products. Besides, products produced by extrusion have a light porous texture with high rehydration capacity. Fractionation of pulses. Recently, pulses have been fractionated into starch and proteins by either wet or dry milling. Milling of whole seed or dehulled seed followed by fractionation of starch and protein-rich fractions will improve utilization of legumes. This method generates products that can be sold as ingredients to food processors and other industrial users. With respect to legume utilization, milling of legumes and fractionation of protein and starch have increased in recent years. Dry milling. In dry milling, pulses are subjected to pin milling twice for obtaining fine grade flour. The pin milled flour is air classified in a spiral air stream and fractionated into light and heavy particles. The fine and light particles contain protein, whereas the coarse and heavier particles mostly contain starch granules. The starch granules remain intact during pin milling, and the process must avoid damage to the starch granules. Although dry processing air classification does not result in as pure protein fractions as wet processing, it is an effluent-free process, and separated fractions are suitable as food ingredient and other uses. Since some protein bodies still adhere to the starch granules at the end of pin milling, it is necessary to reprocess the coarse fraction by pin milling and air classification for increased protein yield. Washing of the air classified starch has also been suggested to remove adhered protein. Wet milling. In wet milling, whole or decorticated seeds are soaked for 10 to 12 hours in water. The soaked seeds are decorticated and milled along with water to produce loose slurry. The slurry is adjusted to a pH from 8.5 to 12 for 1 hour to remove protein from starch. The slurry is then sieved through sieve of specific mesh size depending on size of starch granules in legume. Sediment on the sieve, which is chiefly dietary fiber, is discarded. The liquid portion passing through the sieve is subjected to centrifugation at 3000 G for 10 to 15 minutes. The supernatant obtained is used for recovery of proteins, while as the sediment obtained is washed 2 to 3 times with distilled water and dried at 40 to 45 degrees Celsius to recover storage. For recovery of proteins, the supernatant is adjusted to a pH of 4.5 and then centrifuged at 8000 to 10,000 G for 10 to 15 minutes. The sediment obtained is collected, adjusted to pH 7 and dried as protein. That was all about processing of legumes. Thank you for your patience and keen interest.